Okay, here's a representation of the ionosphere we talked about a little bit. We don't go into it a whole lot because it affects mostly HF, and you have very limited HF privileges. But it's divided into essentially 4 layers. The top layer of the ionosphere, which is the highest one, it's called the F layer, and it has an F1 and F2 sublayer. And they, in the daytime, they kind of appear as separate layers. They tend to merge more at night because there's less activity. Then at the lower layers, we have the E, and then D, which is closest to the Earth. Now, the D layer in the daytime tends to absorb some of the HF signals. So they don't work as well during the day as they do at night, because at night, if you see over here on the shadow of the Earth, that D and E layer have kind of merged and the E layer is almost gone. Okay, so you can get refraction off of the combined F layers at night. So that's why 40 meters works at night much better than it does during the day. You know, there's things like 20 meters, which from what I've seen seems to work about the same regardless.
Universal.
So that's why it makes a difference whether you're talking about daytime or nighttime because of how it affects the ionosphere layers. VHF, we said, is mostly line of sight. There are some propagation modes, which we'll talk about, which utilize the E layer. And we call that sporadic E because it's a very unreliable or sporadic process. And your signal gets dispersed. It's not just refracted, it's kind of diffracted in a lot of different directions. So you only get basically a partial refraction. And you can do that in the 10, 6, and 2 meter bands. Under the right conditions, you can do over the horizon if you're getting some sporadic E layer propagation or dispersion. And 10 meters turns out to be better in the daytime than it is at night if you have sufficient sunspot activity. Now, another 5 or 6 years, nothing's going to work very well at all because the sunspot cycle is going to be at a minimum. So we depend on the sun for lots of things, including radio wave communications. This shows the various layers and how you may go, say, at 10 meters and refract, really should say diffract on the E layer, because part of that signal is going up in all different directions. So part of it gets refracted back down and bounces. It is partially being absorbed in the D layer. So you lose some there, which is why you don't get many, many hops. But you can get some long distances under the right conditions. This one is just showing with different frequencies how it affects it. So your highest frequencies, like your UHF and microwave, they're just going to go straight through all of these with no bending whatsoever. As you get lower and lower in frequency, you get more and more refraction and off of the lower layers. Which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon?
Bravo.
Right. Sporadic E. Uh, oh, this one's just kind of showing typical propagation that you'd see more in HF. And the variation between the what we call the takeoff angle. When an antenna has a radiation pattern, and depending on its height and the type of antenna, how close it is to the ground, affects that radiation pattern. So the higher it is up to a point, the lower that takeoff angle or radiation pattern where most of the energy is. So, and you can see the lower the angle, like at 28 degrees, you're going to get a much larger hop than you do if it was a much higher angle. Okay, just straight geometry. But, you know, when you get up to too high an angle, it either goes through or you have an effect which we call NVIS, near vertical incident scattering. What is S? Near vertical incident something.
Skyway.
Skywave. Okay. Where you can get close in communications. Because one of the things with HF, and you would see it with in the 10-meter band trying to do it as a tech, when you get that refraction, we're talking about fairly long distance hops. But if you wanted to use that technique to talk to your neighbor 10 miles away, you're bouncing right over the top of it. You can use things like NVIS, where you typically lower your antenna very close to the ground, so your takeoff angle is near vertical, and you can get very short hops, let's say, so you can get close distances. Military uses that a lot. They'll have antennas on top of their vehicles, so it's very close to the ground, like a loop, and they get pretty much vertical incident. Some other things that we can have, and we'll talk about, is auroral backscatter, meteor scatter, tropospheric scatter, and tropospheric ducting. So we're a bit far to do auroral backscatter. But if you're like in northern US, Canada, or down, the south end of the earth, you can bounce signals off of the aurora. And the aurora is the Earth's magnetic field reacting with the solar activity, the X-rays, gamma rays, UV, and ionizes that, and it actually causes it to glow, and you see these green, yellow things. It's kind of pretty, and we have one at each pole. Okay, and they're circular because the way the magnetic field lines come out, so it makes kind of a circle around the magnetic pole, not the North Pole. And you get actually more activity if you get solar flares, okay? Assuming the solar flare is not too big. You can get too much of anything, and actually tremendous solar flares can actually wipe out communications because it just way too much radiation. But and I can't explain the physics of how the RF interacts with the aurora, except that it does refract off of it. It's kind of like sporadic E. It's very sporadic. So you couldn't very well do reliable communications that way. This is some pictures from NOAA of and you can see it's much greater in certain areas, like on the nighttime side, both the north and the south. So what is a characteristic of VHF signals received via auroral backscatter? Yeah, I don't think you have to be aimed west. And if it was 10,000 miles or more, we could do it. I don't think we can. Next, we have meteor scatter. There's always meteors coming through the atmosphere, and they leave ion trails behind them, little cylindrical trails that are ionized. And that's what you bounce off of, that meteor trail. Now, they only last for seconds. So it's a very quick communication if you can do it. And people do it. There's a specific meteor scatter mode. And I think I got it wrong before when I said moon bounce. Moon bounce is echo. MSK 144 is specifically for meteor scatter with digital modes. And it's mostly on the 6-meter band. You don't really see much activity there on the other bands. It might be fun to try. What band is best suited for communicating via meteor scatter?
Bravo.
Bravo.
Now they claim it's happened up to 2 minutes. Normally it's seconds. We have tropospheric scatter. Or the troposphere is the lowest region of the atmosphere, like 6 to 10 kilometers. And you can get some scattering on UHF and SHF, which is 10 times the UHF. So UHF, we said, went from 300 to 3,000 megahertz. So SHF is going to go from 3,000 to 30,000, or 3 to 30 gigahertz. And you can operate there. I don't know where you find the equipment.
Yeah.
You can do it. So it's kind of like the other techniques, you're getting scattering, where it's actually dispersing the signal in different directions. So some of it gets scattered back. So that's the portion you see. And because of that, it's a much weaker signal. It's not like you're getting the whole signal refracted. You're getting part of it. And this is just kind of showing the main signal is kind of going right through, and you're getting some scattering. And part of it is, in the direction back towards the Earth. So that's what you have to kind of try to rely on. So it's, again, all of these modes are very unpredictable and unreliable.
So they'd be very distorted when they come through.
Probably. The last one is tropospheric ducting. I would say this is probably a more well, I don't know if reliable is the right word. When it happens, you probably have pretty good communications, but you have to have the right conditions. You have to have an inversion layer where you have a warm layer of air on top of a cold layer to create that duct.
Mm.
And normally you would have the cooler air above the warmer air. So when you get that inversion, and again, I don't know the physics of why that interface causes it to refract, but it does. So the signal can bounce in that duct between the earth and the other side of the duct and back, and you get multiple bounces. They're saying 300 miles or more. I guess I don't know for sure. I can't say I've ever tried it. One of many things yet to try. It's just another thing showing where, and again, it's somewhat frequency dependent. So, and angle dependent on your takeoff angle. So some of the signal is going to go straight through. Some of it's diffracted, but not enough to come back down. And then some of it actually diffracted off of that interface through basically through the duct. So what type of propagation is responsible for allowing over the horizon VHF, UHF communications to ranges of approximately 300 miles on a regular basis?
Alpha.
Can you repeat that?
I'm just gonna go with alpha.
Okay. You chose wisely. What causes tropospheric ducting?
It's Charlie.
Delta.
It's Charlie.
That would be delta.
Bravo. Delta, delta, delta.
Yeah.
That's better. Yeah, this one doesn't have anything to do with sunspots, actually. It's one of the few. Strictly a temperature inversion. And then we talked about precipitation, where any kind of moisture, rain, snow, ice, fog, human bodies, trees, absorbs microwave. And the charts I've seen, it looks like it starts around a gigahertz and starts going up. So it has essentially no effect on the HF band. Maybe a little, I don't think it's quite noticeable on the VHF. Oh, and here's the chart I found. There seems to be a peak here, which I think has to do something with oxygen. And I believe there's another one somewhere, maybe higher up with nitrogen or vice versa. But basically it just shows how the absorption goes up with frequency. What weather condition might decrease range at microwave frequencies?
Charlie.
What is the effect of fog and rain on signals in the 10 and 6 meter bands?
Alpha.
Alpha.
On the 10 and 6 meter band. Where are 10 and 6 meters? Let's see, 10 is HF, right?
Mm.
6 is VHF. Where does absorption start?
Oh, trick question.
That was my second choice.
Just remember that for the test.
Oh, now he's gonna mess me up because then they'll start really thinking and I'm like, hey,
Okay, so we learned that sporadic E on the 10, 6, and 2 meter bands lets you do some over the horizon sporadically. Auroral backscatter can be done with a distorted varying signal strength. Again, it's kind of a backscatter like sporadic E. It's a sporadic thing, not dependable, not necessarily a nice signal. Meteor scatter, similar. You're bouncing off of the meteor trail. So you have to know when there's a meteor and catch the trail for the few seconds that it lasts. Now they claim up to 2 minutes. I guess if you had a big enough meteor, trail might last long enough before it burned up. Tropospheric ducting, where you're refracting off of that inversion layer in the Earth. So you can go that, what was it, 300 miles, I think, which is the most reliable of those. And then precipitation, absorbing microwaves and a little bit of UHF, but basically microwaves.